let's say you're on that bike ride again, and there's this big hill in front of you, and you could go over it to get where you're going. Or it turns out there's another route that goes around the hill and eventually gets to where you're going. Let's face it, if you're offered that, it is a lot more likely you're going to do the bike ride. So what we have is sometimes we have a very large activation energy standing in the direct route of getting something done. And if we add a catalyst, we give a reaction an alternate pathway to completion. Now, we define a catalyst, and this includes things like enzymes, as a substance that will increase the rate of a reaction but not be consumed. Now, how could that happen? We know that our rate constant K is made out of A and then E raised to this power. So usually it happens because E sub A has been lowered, but it can also happen because A has been increased. A, you remember, has to do with the directions that things combine. So how likely are they to hit in the right orientation? But here we have ozone changing into diatomic oxygen. This blue path would be if the two just slammed into each other with a lot of energy in order to make this happen as a result of the collision. This is the one that is catalyzed. In this case, we're considering the catalyst to be the ultraviolet light. Technically, this is a catalyst because even though it's not a substance, it made it happen faster. It didn't get consumed because it wasn't a substance, but it did get some consumed because it's energy. It's a little complicated, but this is the example that if we use the ultraviolet light, there's a much more quick method of getting from point A to point B, of changing that ozone into diatomic oxygen. Now, we were talking about A being changed, and we have a wonderful example of that in your car's catalytic converter, because your catalytic converter has this baffle of honeycomb shaped so that vapors that come off of your car engine have to go through here, and it's made in such a way that they have to snake their way through, and so they are not going to get through without hitting this catalyst, which is usually made out of platinum. What it will do is this nitrogen monoxide, which we don't want to get into the atmosphere because of all the other things that it then spawns. Think back to the very beginning of the chapter of all the different things that would happen after the nitrogen monoxide was created. It adheres to the platinum catalyst, and then it's in a two-dimensional space so that it becomes incredibly more likely the nitrogens will meet and the oxygens will meet, and they'll just separate. And once they have turned into the nitrogen and oxygen, they're no longer very attracted to the platinum, so they let go and they go back into the atmosphere as nitrogen and oxygen, which is what we want them to be in the atmosphere. So this gives an alternate pathway for it by making sure that the collision will be in the correct orientation every time. And so it will take care of the issue, and your exhaust will be clean instead of obnoxious. I should just say noxious gases, but I think they are obnoxious. So these gas phase reactions are taking place on catalysts. What's this business about heterogeneous? Oh, it's a different phase. Because you see, these were gases. The platinum is a solid, so it's in a different phase. So we call it a heterogeneous catalyst. An awful lot of the enzymes in your body they're like aqueous, and they're working on other aqueous things, and so everything's in the same phase, and that would be a homogeneous catalyst. So in the same phases, the things that are reacting. The other interesting thing is when you have these gas phase reactions on a heterogeneous catalyst, they exhibit zero order kinetics. The important thing isn't how many gases there are. The important thing is how much catalyst you have. Do you have enough surface area? And that's why these things have layers and layers of baffles, to try to make sure you have enough surface area to take care of all the nitrogen monoxide. So now you know a little something about how your catalytic converter works.